We'll get started in a minute. I apologize for the delay. Feedback there. Hey, good morning, and let's get started. So as you know, we're gonna have our first exam on Monday, September 27th. And today, what I want to do is to talk a little bit about the format of the exam and the material that is going to be covered. And I brought some problems from the assignments for discussion. So we will go through some of the problems in the assignments, and then we will open the floor for questions. And then again, you to understand that the exam is going to be in class, so you have to come on Monday to the classroom to take the exam. Okay, so you need to be physically present in the classroom on Monday for the exam. So you're going to have an hour and 20 minutes to work on the exam, which is the class period. The exam is going to be designed, should take less than that. So you have some cushion time for completing the exam and make revisions. And the exam has two parts or two sections. I call them sections. Section 1, there are 10 questions that can be multiple choice or true or false questions. These are questions that are based on our discussion, definitions, concepts that we mentioned through the first part of the semester. They can come from any of the lectures. These are going to be things that you know. I just want to make sure that you are clear on those concepts. So the questions should not be difficult. They are not tricky questions. They are just there for me to make sure that you're understanding the important concept for this first part of the course material. And so these are 2 points each, so 20 points on the first section. Again, do not overthink these questions. Should be simple. You understand the concept, you read the question, you should be able to answer it correctly. I'm not going to make questions they try to take points out of your exam. And then the second section is where you are going to be solving problems. These could be short answer, or it could be explanation, description, or mathematical. In this first part of the semester, I mean, these are problems that similar to the ones that you solve in the class and also in the labs and in the assignments. So you should expect problems like applying the Gauss-Jordan method. That should be one of the problems. So you can obtain a solution, and then you can tell me whether or not that solution is unique, or is it's not feasible, or no solution. So after you solve the problem, you should make a conclusion in terms of what type of solution you're having. Formulation. So we spend a lot of time going through several applications in which you are formulating linear programming models. So we discuss the diet problem, production planning, scheduling problems, project planning, and so on. So if you're familiar with those formulations, then you should be fine. Formulation will be there. My advice is to work on the exam, all the problems of the exam, and then leave the formulation for the end, because typically, I mean, some students will find that a little challenging. So if you complete the exam and then you leave these problems to the end, you'll be spending the rest of your time trying to formulate the problem. What I'm looking for is, I'm not looking for a perfect formulation. Basically, I want to see that you're able to describe the decision variables, right? These are the decision variables. And then state the objective function clearly. I'm going to maximize or I'm going to minimize this. And then there are going to be some constraints. Formulations, again, you can formulate the same problem in different ways. So that's what I mean. Perfect formulation maybe does not exist. So long as you cover the restrictions in terms of resource limitations and then the non-negativity constraints for your decision variables. So these decision variables are greater or equal to 0. Another type of problem that you can expect. So we talk about graphical method, solving problems using the graphical method. So make sure that you understand. Again, I'm going to make the exam in a way that you can build this quickly. So there's not going to be a lot of complicated constraints. You will have to graph the constraints and the objective function in order to find the optimal solution. So graphical method, and then another type of question that I can ask is for you to set up a linear programming model into standard form. So I give you a formulation and I ask you, okay, this is the formulation. Can you set up this into the standard form? Which is what we discussed in our previous lecture. So in general, those are the type of questions that you will expect in this section 2, which again are similar to what we've been doing in class for the first part of the semester. So the lectures, you have a question? Okay, the lectures that we covered during this first part of the semester, we started with the review of linear algebra. So understanding matrices and vectors, what is a set of or a system of linear equations, how to apply the Gauss-Jordan method for solving systems of linear equations, difference between linear independence and linear dependence, what is the inverse of the matrix, and what are determinants. So we discussed this in detail. Again, this is a review, but I mean, in addition to test the Gauss-Jordan method, which I always, from the beginning, have been saying that this is very important. So I need you to be well prepared in terms of applying the Gauss-Jordan method. So I have to test that in the exam. The rest of the material will be more in terms of questions that can be included in the first section of the exam. So what is the difference between linear dependence and independence, and so on. And then lecture 2, we started our operation research material. So we talk about formulating 2 decision variable problems. And then we also talk about the difference. What is a feasible region? How to use find the optimal solution using the graphical method, and we solve problems using the graphical solution method. We also talk about, in both cases, using the Gauss-Jordan method, we talk about how to identify the different type of solutions. So multiple solutions, unique solution, no solution, unbound solution, those 4 type of solutions. We also can do that with the graphical method. So should be aware of the special cases in which you have alternative or multiple optimal solutions, when the problem is infeasible and when the problem is unbound. So infeasible means that there's no possible solution. There's no, after you set up the constraints, there's no an area in which you can meet all the constraints. So you will not be able to find a solution for that problem. So when you substitute any combination of values for x1 and x2, you cannot find a combination of x1 and x2 that will meet all the constraints. That's an infeasible problem. An unbound problem is you can find a solution, but the solution keeps growing as you move toward the direction of improvement. So there's no bounds. So the optimal solution will be in infinity. So that's an unbound solution. So you have constraints, but the direction of improvement in terms of the objective function is pointing you to an area that has no bounds. So you will end up getting a very big number or an infinite solution, infinite value solution for one of your decision variables. So that's an unbound solution. So that's a graphical solution to LP problems. Any questions so far? Good. And then the formulation of linear programming problems. So we talk about what is linear programming, the guidelines for model formulation, and then we went through the example, the diet problem, production planning, inventory control, multi-period production planning, inventory control, manpower planning. We discussed the bus scheduling problem and the post office problem. We have lab in which you have to formulate a different application related to scheduling. We talk about the urban development planning. And finally, the blending and refining. Okay, so those were the examples that we studied in terms of formulation. And again, the problem in which you're going to have to formulate will be part of the exam, but it will be a formulation that will resemble one of these applications that we discussed. Blending and refining, in the lecture, I mentioned that this is very important, but it's not going to be a formulation like that one, because that one is very challenging. It's time consuming. It's not challenging, but very time consuming. So blending and refining, don't worry about that one. The other ones are more feasible in terms of a formulation problem for the exam. And then lecture 4 was in terms of the simplex algorithm. So we started the discussion of the algorithm, basic setting up the formulation in a way that we can apply the method. And also we talk about how the method works. How is the search being performed for obtaining the optimal solution from our problem. So we talk about converting an LP to standard form, and then the transition from graphical to algebraic solution, and the use of basics and non-basic variables, identifying how many basics and non-basic variables based on the number of decision variables and constraints. So N is the number of decision variables, M is the number of constraints. So we look at the difference, N minus M. That difference is going to tell you how many basic variables you will have in your problem. So if you have 4 decision variables and 2 constraints, then you will have 4 minus 2 non-basic variables. So you can assign values equal to 0 to the non-basic variables and solve for the basic variables to find one of your corner points. And what we want to do is we want to find all the corner points, because we know that the optimal solution will be on one of those corner points in your feasible region. So the idea is you have these corner points. The simplex algorithm will perform a search on your feasible region looking at the corner points. And it's going to use this relation between points in terms of which, if these 2 points share basic variables, then we know that they are adjacent to each other. So if you want to search a direction of improvement, you can use that information to move from one point to a closer point to see if you can improve the solution that you have on hand. So we will talk more in detail about this after the exam. But up to here is what we are going to see in the first exam this semester. Again, 4 lectures. All the information is posted in the modules in Canvas. So I have posted the lecture material with the notes, the solutions for the assignments and the labs. So everything should be there for you to prepare well for the exam. So how to prepare for the exam, study the lecture slides, the labs, and the assignments or the homework. Let's go close attention to those problems that we assign and the ones that we cover in class. If you have a good understanding of how to solve those, then you should be in good shape for the exam. The exam is going to be closed book and notes. I will allow you to bring a calculator. So if you feel more comfortable bringing a calculator for the computations, you can do that. I want to emphasize that you need to show your work as clearly as possible. In case that you end up providing a wrong solution, if you show me your work, I can provide you with partial credit, but that I can only do that if you show me the steps. So make sure that you show your work, formulas using your solution. For example, if you're solving using the graphical method that you show me, okay, these are the points that I found for each constraint, and then you plot the constraints. So things like that can help me award full and partial credit for your solution. So far, this is in terms of the format and in terms of the material that is going to be included in the exam. These first 4 slides of the review are covering that portion. On the next slides, what I have are some problems that I want to discuss with you just for review purposes. But before I do that, I want to know if there's any questions. Yes.
So you said for the first part, multiple choice.
Multiple choice or true or false? Or true or false. It could be any, I mean, I haven't finalized the design of the exam yet. I'll be working on that this week. But it could be either multiple choice or true or false. It's not going to be combined. So if it is multiple choice, all questions will be multiple choice. If it's true or false, it will be all questions true or false.
Is that more related to lecture 2?
This question can come from all lectures, from lecture 1 through lecture 4. So these are going to be concepts, like I mentioned, linear dependence versus linearly independent. What is the difference? That could be a question. Things like what are basic variables, what are non-basic variables. In terms of formulations, what is the decision variable? What is the objective function? I can ask questions in many ways. But everything related to the material that we cover in those 4 lectures. That answer your question? Okay. So I want to spend some time doing some over some of the problems in the assignments. I know this one brought some questions last time, so I'm showing the problem, and then I want to include some additional information here for the solution. So here we have a company that operates 10 hours a day, manufactures 2 products on 3 sequential processes. Following table summarizes the data of the problem. So we have the minutes per unit per process, and we have 2 products, and we have the profit per unit for each product. So the question that we are trying to answer is how many daily units of product 1 we need to produce and how many units of product 2 we need to produce. So those are my decision variables. And they are listed here at the top. And then my profit is what I'm going to use for my objective function. So in my objective function, I'm maximizing this profit, $2 per X1, which is product 1 daily units, and $3 for product 2 X2, which is the number of units that I'm going to produce for product number 2. Okay. So I guess I omit some of the information. So we have some additional information in terms of the number of hours that are available per process. So it's 600 hours for, I mean, 600 minutes per for each one of the processes. Was that part of the assignment? Did that piece was included? So maybe when I copy the problem in here, I didn't include it. So I apologize for that. So we have 600 minutes per process, and we want to formulate this constraints per process, which is what we have here. So per process, we have 600 minutes, and we have the requirements per product. So 10 minutes for process one, and for product number one, and 5 minutes for product number two. And that's our first constraint. Second constraint for process number two, requirement 6 minutes and 20 minutes, and so on. And then we have to make sure that we have these non-negativity constraints. So to solve the problem using the graphical method, then we have to plot each one of these constraints. So that process we would discuss, we have to find 2 points for each one of the constraints. So you can do that by setting up, let's do 10x1. So if I want to find 2 points for 10x1, 5x2, I can make x1 equal to 0 and then solve for x2, right? So x2, if I substitute 0 here, then I'm gonna have 5x2 equals 600, and then x2 equals how much? 120. So this is gonna be my first point. And then I can do the same thing. I can make x2 equal 0. So my first point is going to be 0 and 120. I can make x2 equal 0 and then solve for x1. So if I do that, then I have 10x1 equals 600, and this is going to be equal to 60. So my second point is 60, 0. So if you go to this line, this is going to be your first point, 120, 0. I'm sorry, the opposite, 0, 120. Let me fix that. And then your second point for that constraint is this one, is 60 and 0. And then using those 2 points, you can draw this line. And you repeat that process for each constraint, right? So you do it for constraint number 2, number 3, and that's what we have here. We have all the constraints plotted into this. This should be for constraint number 2. If I let x1 equal 0, then this is going to be 30. So this is 0 and 30. And then this is going to be 100, 100, and 0. So using those 2 points, I can plot this other line. So after plotting all those lines, I get the feasible region, which is the area where all constraints are satisfied. And I know that using this information, I can find the optimal solution in this region. To find the optimal solution, I have to use the objective function. Okay, so to find the a line here. So let me state this. So this is the isoprofit line, 2x1 plus 3x2. I need to find that isoprofit line. This is what I'm going to use to find the optimal solution in my problem. And I'm using the objective function. So I need to find 2 points to plot this line. What I typically do is I find a point in the feasible region. To find my first point, I choose a point in the feasible region. Could be any point in the feasible region. So for example, I can choose 10, 10. I know 10, 10 is going to be there. So if I choose point 1, 10, 10, and I substitute that in my objective function, this is going to be z equals to 2 times 10 plus 3 times 10. So this is equal to 50. I have a point that is going to give me an objective function equal to 50. So now what I need to do is I need to find a second point that is going to give me the same objective function. So basically what I need now is a second point. I don't know what that point is, but whatever that point or end up being, it has to be a point that when I substitute the values here is going to be equal to 50. And then this will be a problem that you can find a point easily, like 2 times 25 would be a combination that you can use. So if I choose point 25 and 0, 25 and 0 is going to be equal to 50. So now I have 2 points that I can use to plot this isoprofit line. So point 1 is 10, 10. So I'm using this, trying to scale this as much as possible. So 1, 2, 3, 6. So this will be 10, 10. And 25 and 0. So 10, 20, 25. This will be the other point. If I draw that isoprofit line like this, if I move that isoprofit line in this direction, the last point that is going to touch is this point. If you move that isoprofit line in that direction, which end up being the optimal solution. That's how you identify the optimal solution. Okay. I know that finding that point is difficult. Like here the value for that point is difficult, is a fractional number. Yes, I understand that. But if you can identify the point using the graphical method and you tell me it's this point, even if you don't get those exact numbers, the answer will be right. Okay, I understand that you have a limitation in your computational capability to get there. But what I'm more interested is in you showing me that you can find that point using the graphical method. As long as you show me the right point, then you should be able to get the solution. Does that make sense? Okay.
So like if we were like, let's say we had this one on the pad.
Yes.
We said at this point, I guesstimated, I said 50.
Yes. Yes, based on your scale, this is the point. Yes, that'll be correct. Okay.
This is formulating and solving.
This is formulating and solving. Yes, this is the graphical method. So I'm asking you to solve a problem using the graphical method. And it's going to be clear in the exam. Use the graphical method to formulate and solve using the graphical method. Just one problem. You don't have to solve, like if I ask you to formulate, just formulate. Okay? Sorry. Yes. Oh, yes. Thank you. Oh, so the question I got from the chat is, where did the 600 come from? So the answer for that is, when I copy the statement of the problem into the PowerPoint, I forgot to include the sentence that stated that you have 600 units per process. If you go to the assignment, this is a problem coming from the assignment, so you should see that value or that statement in the assignment. So it was my mistake. I didn't include the statement in the review slides. Oh, okay. Okay. Yeah, thank you. So it operates for 10 hours. Sorry, yes. Yes, so it's a conversion into minutes for the 10 hours that we're given. Thank you. Okay, so good. So we understand this. The other two problems that I'm showing on the next slides are solved using the same method. So here we have another example. In this one, again, you have to go through the process of setting up the constraints. So again, you have decision variables, the objective function, and the constraints. In this case, we have some bounds for the decision variables. So in addition to be greater or equal to 0, they're also limited in terms of how high they can be. And then when we plot the constraints, we have one constraint for the bounds for x2, one constraint for the bounds of x1, and then we have this constraint, which is this one that goes cutting those two. So again, in order to know that this is the optimal solution, we have to find the isoprofit line. So we have to go through the same process, sorry, z equals 40 x1 plus 35 x2. And we have to find a point inside this feasible region. So this will be 400. I'm sorry, no, this will be 550. So this gonna be, so like an estimate 275. And this one is 580. So yeah, so in the middle. So anyway, so we can choose a point in the feasible region. I tend to use points that are simple to compute. One, so we go through the same process. We can show 10, and this is 400 plus 350, and this is 750. So I now have to find another point that when I substitute the numbers here, 20 times something plus 35 times something, give me 750. Can we find a combination easily here? Yeah, so this, yes, 750. So again, you will find that second point. Yeah, there's no way for me to divide 35 and by 750 and get an integer number. So these numbers will be fractional values. Maybe if I choose another combination. Okay, so can anybody tell me how much would be if I make this 750 divided by 40, how much that is? 80? 750 to
18.75.
80,
No,
18,
180.
18.75. Okay, so 18.75. So 0.2 is 18.75 and 0. So now I have 2 points. I can plug that into this. So this is 550, 250, 290 in the middle. So I have, say this is 100, and this is 100. So going in this, we have 18 point, will be something like this. Yeah, very difficult to map this in that scale.
Can you use the full color?
Yes. So I'm trying to plot those 2 points in this area. So let's say this is 8.75 and this is 10. So the curve should be something like this. Because 1010 is lower. I'm sorry, this should be around here. 1010 is lower than 18. So when you move in this direction, the last point that you should be touching is this point right here. And that will be your optimal solution. Again, in the exam, plotting this will be a lot easier, okay? Show me that you know how to implement the method is the goal, not to do the math. It's just to show me that you know how to do the method. So you find the isoprofit line using these 2 points. So isoprofit line with 2 points, 10, 10, and 18.75, 0. You use those 2 points to draw a line, which is this line, and then you move that line in the direction of improvement. You find the last point that is touched by that line, and that's the optimal solution. And I think on the next example, yes, go ahead. The objective function?
Yeah.
The first constraint, x1 divided by 800, 6x, okay. So the maximum production capacity is estimated at 800 sheets of 600 bars per day. So this looks like the lab that we did in the class for the trucks production. You have aluminum sheets and aluminum bars, and then you have a maximum production capacity. If you use your manufacturing plant only to produce aluminum sheets, you will be able to do 800. If you use your production plant just to produce bars, then you'll be able to produce 600. So the question is, what fraction of the plant, or how many of each you will be producing to make sure that you use 100% of your plant capacity? So what you have on x1 over 800 is the fraction of sheets, aluminum sheets that you'll be producing. That fraction is going to tell you how much capacity you'll be using to produce aluminum sheets. And x2 over 600, you know, the maximum number of bars that you can produce at full capacity is 600. So when you divide that by x2 divided by 600 is the fraction of bars that you're going to be producing. The summation of the two should not exceed the total capacity of your plant, which is 100. Yeah. So again, this is similar to that lab that we did in class for the trucks. Same strategy.
Our optimal solution.
The optimal solution. 600, 550, 550, yes. Yes, because we have a limited number, that the maximum number of sheets that you can produce is 550. And 580 for the box. Yes. So X2 is 187.
Just 80 for the profit per ton is 40, I mean, not about the ton here, I mean, I know what it's the ton, but I'm just not. So it's usually the profit
Per ton is 40 per sheet. And 335 per box.
So each one ton.
Okay, I see what you're saying. So that amount of material or amount of, yes, you are saying, so the price is depending on how many tons you're selling, right? Is that what this statement is saying? Profit per ton is $40 per sheet and $35 per bar. But we don't have information about how much each sheet is weight. It's so based on that information, we cannot do a weight combination for estimating the profit. But I see your point. Yeah. So the profit per sheet will be $40 and per bar will be $35. So that's why we end up producing more sheets, right? Because it's more profitable for the system. But we have a capacity limitation for that product, or a demand limitation, I guess, for that product. I'm not going to go into the details of this one. It's the same way. In this one, we have I think this is the isoprofit already plotted. So that's the isoprofit line that is used to identify the optimal solution. And then I have some problems here for formulation. The production for products are processed sequentially on 3 machines following the table. The pertinent data of the problem is given. So we have the manufacturing time per hour per unit, and the machines, the cost per hour per machine, and the time it takes per product, and the capacity limitation for the machine hours, and the unit selling price. So this, again, looks like one of the models that we already solved. We have the decision variables, the number of units produced of product J. We have 4 products. And in order to find the profit per unit, we had to take into account the unit selling price and the cost per hour for the machines. So that's what we are doing per product. For product 1, we end up getting $12, product 2, $18, product 3, $2, and product 4, $11. So the objective function is to maximize the profit. And then we have capacity limitation constraints for each machine. So those are our constraints. Sorry. So this is for machine 1, machine 2, and machine 3. And then we have the non-negativity constraints for the decision method. Okay, so 3 machines, capacity for each machine. Those are my constraints. I guess the challenge here is to compute the profit per unit, which involves the unit selling price minus the cost of production. In this one, we have 3 models and a certain product using raw materials A and B. The following table gives the data for the problem. So the requirements per product in terms of raw materials and the availability of the raw materials, in this product, again, similar to the previous one, we have the price per unit. And in addition to that, we have the minimum demand. So we don't have information about the cost, so that will be, oh yes, see. The labor time per unit of Model 1 is twice that of 2 and 3 times of that of 3. The tail labor force of the factory can produce an equivalent of 1,500 units of Model 1. Market requirements specify the ratios 3 to 5 for the production of the 3 respective models. Okay, so in this one, we have a set of ratios that are used to specify our production. So we have the 3 times that of 3, and the entire labor force of the factory can produce the equivalent of 1,500 units of Model 1. So starting with the decision variables, we have the number of units per model, and we have 3 models. So we have XJ, with J equals 1, 2, and 3. Maximize the profit is our objective function. So the profit is given per price per unit. And then we have the constraints in terms of the raw material availability. So 4,000 for raw material A and 6,000 for raw material B. So those 2 constraints are easy to formulate. Then we look at the labor time per unit. So the ratios are, Model 1 is twice that of 2. So we use 1 as our measurement for the ratio. So this is going to be 1. And it's saying that it's twice that of 2. So it means that for 2, we need half of the time that we need for 1. And 3 times of that of 3. So again, 1/3 of 1. So that's why we have these ratios here associated with the entire labor force, which is 1,500. And then we have market requirements specify the ratios 3 to 5 for the production of the 3 respective models. Yes.
So regarding constraint number 3,
Yes.
it's saying the labor time per unit is this, and then 1,500 is a number of units. So how come they make time equal to units?
The labor time per unit.
So
Yeah, so we have that piece here that is associated to the number of units of Model 1.
labor time per unit.
Mhm.
So the left side of this chain will be 10. And then the right side, which is 1,500, will be number of units.
Is the labor time per unit is twice that of 2 and 3 times that of 3. So equivalent of, so basically the equivalent of the factory can produce an equivalent of 1,500 units of Model 1. So the total time that you will have available is equivalent to producing this many units of Model 1. So that's why we are using Model 1 as our standard measurement. So it doesn't specify how much time you have available, you're right. But it specifies that the time that you have available allows you to produce this many units of Model 1. So when we set up the constraint in terms of time, we are using Model 1 as our equivalent measurement. Does that make sense? So the time or the capacity or the entire labor force that you have available is equivalent to this many units of Model 1. So let's say it takes you a minute to produce Model 1, then you will have 1,500 minutes.
Yeah, but it's a 1,500 minutes.
Yes, and that's assuming that. So basically what I'm trying to say is that time can be canceled out when you are looking at the at the overall process. So this is 1,500 units, right? And that's your labor force. 1,500 units. So your capacity for production is stated in terms of how many units you can produce on model 1. It's not attaching a time figure to it, right? Same thing for the labor time. Yeah. Yeah.
I confused. It's on the left side, we have basically unit per time, which is time multiplied by unit. So we can time per unit. And then it doesn't equal to units. So it's kind of hard to come up with this constraint this way.
Okay.
You know what I'm saying?
So labor time per unit.
You can the same thing you could expect the third constraint will be less or equal to 1.
So the way this is stated, let's say model 1 time per unit, right? But we don't know if this is minutes or seconds or hours, right? It's time unit. And then the labor force see if I can set up this in a unit that will cancel out. So 1,500 units on model 1. So if I say time will be equivalent to 1,500 units of model 1. And if I know this is times and trying to see if I can show you this mathematically. I don't know if that's going to help or not. So if I solve for the units, this will come up here at the bottom. And then you will have this by itself. So if you look at the previous problem, we are essentially doing the same thing. We are assuming that the capacity is stated in terms that are not associated with the time. It's stated in terms of the capacity of production. Yeah, and this is
I guess but it's just hard to come up with it. Honestly, if I have this, I wouldn't do it like that.
okay.
I mean, now since I see the solution, going through this like
Yeah.
5 times, I can do it.
I can relate to that, and that's okay. It's not that I expect you to come up with this type of constraints the first time that you see these type of problems, but as you get into learning different models and different formulations, these things will come up to you quickly. I say, okay, remember that problem that we have a similar statement, we can formulate it this way. I understand that. I can relate to that. You have a question?
No, I was going to say in the beginning you mentioned you will not have something to kind of make us confused.
No. Yes, and that's a good point. So I'm not going to ask you to formulate a tricky problem. Like I'm not saying this is tricky, but I know this will take you some time to come up with a statement like this. Will take you a long period of time. So I'm not going to be putting something like that in the exam. Okay.
Yeah, because
I know you're capable of doing it if you have other materials to refer to, or and again, it's this as we discussed in this lecture for formulation, these type of things comes with practice and seeing different examples like the chess, you see different moves and you learn those and you use them as you learn more about the process. But those are, yeah, good points, good questions.
If I would have this an exam, I would come up with a constraint. I would use this, the number 3 is the left part, and I would make it less or equal to 1 because of time, you know. And
So this constraint,
yeah,
less than or equal to 1 in terms of,
because we're talking about time, units of time. But now, I understood that we assuming that 1 unit of time.
because you have to associate it with how the capacity is defined for your resource. And in this case, the capacity is defined in terms of model 1. So remember, on the right-hand side of the constraints, what you want to put is your capacity limitation for all these constraints. So in this case, for that particular part of the model, that capacity limitation is stated in terms of model 1. So that will be your right-hand side. And then the work will be to, or the challenge will be to make the left-hand side consistent with how the right-hand side is stated. Okay. See. Okay, we're good. Another formulation. This is a production, multi-period production scheduling problem, and it follows a similar formulation that we cover in class. So we have an inventory cost, we have multi-periods, and we are deciding if we are going to be producing more than we need per period. And if that's the case, then there's going to be a cost associated with the inventory at the end of each quarter. You want me to go in detail about this one, or? Yes, so let's look at this one. So we have the demand for an item over the next 4 quarters, 300, 400, 450, and 250. The price per unit starts at $20 in the first quarter and increased by $2. So the price is $20 in the first quarter and increases by $2 each quarter thereafter. So this is $22, $24, and $26. The supplier can provide no more than 400 units in any one quarter. Okay, so we have a capacity limitation, maximum 400 per quarter. And although we can take advantage of lower prices in earlier quarters, the storage cost of 3.5 or 350 is incurred per unit per quarter. So inventory cost per quarter. In addition, the maximum number of units that can be held over from one quarter to the next cannot exceed 100. So your inventory is going to be limited to 100. Develop an LP to determine the optimum schedule for purchasing the item to meet the demand. Okay, so we have $20 cost or price per unit. The price per unit start at $20 in first quarter and increases $2. Yep. So we are trying to minimize our cost of producing these items, right? So we have a price associated with producing in each quarter, and we have a price associated with the inventory. So our goal again is to minimize the total cost, which is the summation of producing this many units in each quarter plus the inventory cost, which is 350 per inventory that you carry in every time period. Then, if you remember that line that we draw, we are now having a demand here. Okay, we have the demand. Good. Demand is 300. Demand is 400. 450 and 250. So we are trying to meet this demand, and we are deciding how much we are going to produce in X1 and how much is going to go into inventory, and then X2, and how much is going to go to inventory 1, 2, X3, inventory 3, and then X4. Okay, so that's our problem. We want to know what will be the best schedule in terms of production and inventory. So we start with X1. We are going to state a constraint for each period, right? So the first period, basically what it's saying is we have X1 plus minus oops. So X1 is one I'm producing minus the 300 has to be equal to what I'm going to carry on inventory, or so whatever I'm producing minus the things that I'm going to sell, well, the difference will be equal to the inventory, right? And then you follow the same process for each one of the constraints. So you have X2 plus whatever is coming as inventory from 1 minus 400 is going to be equal to my second inventory. Yes.
We can also do it differently, right? I mean, in terms of the first one, so the capacity is 400, we can produce 400 on the X1.
Produce 400?
Oh, so we cannot exceed 100.
Yes.
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 Yes, okay.
And then you follow the same strategy for the rest of the periods. And then you add the limitations in terms of the maximum that you can produce per quarter. So that will be this constraint, 400 maximum inventory. And we are saying that these two are going to be equal to 0 because you start with 0 and then you don't need to carry an inventory for I4 because you are done in period 4. So that's not needed in the way that we formulated this. We are not using a decision variable I0 or I4.
So isn't that we carry over that we have the things that they will let the storage, carry them over so you minimize the device instead of buying 250 and not buying 150.
So I3 is covering that inventory. I3 is covering the inventory that is carried to period 4. Okay, so anything that you're carrying to as inventory for that last period is covered by I3. But then you don't want to produce more than 250 minus the inventory because your production schedule ends in 250. So at this point, you're done. if you produce more, let's say you produce X4, you have an inventory of I1, I3 equals 100. You want to produce 150. You don't want to produce more than that because you just want to cover that demand. If you produce more, that's going to be carryover, but you don't need it. Okay, so it's an extra cost that is unnecessary. Okay. Yes, so this right here is basically saying the same thing that I4, which is what's going to go here, is going to be equal to 0 because you don't want to produce more than what you need. Same thing here is basically saying that you start with an inventory of 0 because there's no production associated with it. No, no. I mean, if remember, it's going to be associated with how you define your decision variables. So if you just define xi, x1, x2, x3, and x4, and then I1, I2, and I3, if those are your decision variables, which you can formulate the model with those only, you don't have to specify a value for I0 and I4. Okay, good. It seems that they did that. You see this, they're doing the bounds for I equals 4, 1, 2, 3, 4. So 0 is not part of that set. Okay, here we have some scheduling problem. And similar to the problems that we cover in class, we have the number, an hospital employs volunteers to staff the reception desk between 8 and 10 p.m. Each volunteer works 3 consecutive hours, except for those starting at 8 p.m. who work 2 hours only. The minimum need for volunteers is approximated by a function over 2-hour intervals, 8 to a.m. Yes.
So problem number 8, that means that.
Yeah, so anybody have questions about this one? Yeah, you want to go over it? Let's do, I mean, don't worry, we can continue until 11 if we need to, in case you have to move to the next class. So the idea is, again, you have a step function of 2 hours starting at 8 a.m. and as 4, 6, 8, 6, 8, 4, 6, and 8, because most volunteers are retired individuals that are willing to offer their services at any hour of the day. However, because the large number of charities competing for their service, the number needed must be kept as slow as possible. So again, the idea is to know how many people will be starting at each shift. We have shifts that are 3 consecutive hours, except for those starting at 8 p.m. So this one is 2 hours. And then, however, because, okay, so we want to minimize the number of people that are going to be scheduled during the day. So that's our objective function. And we have xi representing the number of volunteers starting at hour I. So if you remember this again, the way that you go about this is to create a table in which you're going to state the number of hours and you're going to identify who's going to be working on each time period based on when they're starting. Okay, so for example, if we do 8, 9, 10, 11, 12, 1, 2, 5, 6, 7, 8. We have 8, 9, 10, 11, 12, 2, 4, 7, 8. And then we look at, if you start at 8, you're going to be working 3 shifts, 3 hours consecutively. So you're going to be working these 3 hours. If you start at 9, you're going to be working these 3 hours. You start at 10, working these 3 hours. You start at 11. This is 10, this is 11. So as you move farther into the schedule, you'll see how this is going to be trending toward your right. And then to formulate the constraints, you start looking at the columns. So for example, at 8 a.m., you only have the people who started at 8. So that's why X1 will be by itself. And then on the second hour, you have these two. So X1 plus X2 will be greater or equal to that number, and so on. But creating this chart is what's going to help you come up with the constraints. Mm-hmm.
So that each one will be greater before.
Yes.
And then 9 a.m. become X1 plus X2. So same. So make it X2 0 because one is already greater.
Yes, but remember that X1 is going to end up the shift at 10, and then X2 can help you cover the hours that follows, like 11 and 10. So yeah. So that's the thing about scheduling. Sometimes you would add resources earlier just to make sure that you cover the hours that are coming afterwards. And that could be a solution. I'm not saying that that is not a possible solution, but I cannot tell you that that would be the optimal solution. We will have to see at all the possible combinations. And remember that this is,
I mean,
yeah.
like 8 p.m. we have 2 people at least.
Mm-hmm.
And 9 p.m. we keep 4 people at least.
Yeah, so yeah, the problem is forcing you to have 4, that's right. So if you don't schedule anybody at 9, let's say the second shift is 0, then you will still have 4 people in the second hour. That's right. Then at 10, you still have 4. Say, okay, you have to add 2, but then you cannot. Shift 2 is gone, right? So you're gonna have to add it with shift 3. Yeah. Yeah. So that basically saying I'm not going to start anybody at 9, so that shift is gone. I will have, if I need more people, I will have to have people using a different shift. Okay. Okay, so let's see the next one. This one is similar to what we did with the previous one. You're talking about one in particular, this one. Okay. This one. Okay. So trucking company, terminal docs include casual workers who are hired temporarily to account for peak loads. At the Omaha, Nebraska dock, the minimum demand for casual workers during the 7 days of the week, starting on Monday, is 20, 14, 10, 15, 12, 18, 10, and 12. Each worker is contracted to work 5 consecutive days. Develop the LP model. Yes, go ahead.
Yes, when I was going to film, I started the point where I was trying to figure out why do we, like for example, for first constraint where we have the people for Monday shift.
Okay, so I guess the order in which these ones are set up, is that what's confusing? Like, why don't we start on Monday and do this, and this, right? That's a good question. And let's see if there's anything specifically here. The minimum demand for casual workers 7 days a week, starting on Monday, is 20. So this is the demand for Monday. Okay. Each worker is contracted to work 5 consecutive days. Okay. Yeah, that's a good question. I guess.
understanding that we are talking about finishing.
Mm-hmm.
Finishing, but the questions say started at one.
Starting on Monday, it's going.
Okay.
From Monday to Friday, and that is the 5 days, and then for X2, it starts on Tuesday.
Oh, yeah.
And then it goes down.
Thank you. So that's,
I was confused at first too, and then I was like, oh.
yeah, it's because maybe the way I set up the problems in class is the opposite way.
I think so too, I think that's-
Yeah. Yeah, so if you invert this matrix, you will end up with the same order. So what this is saying is for X1, you're working Monday, because you're starting on Monday, you're working Monday, Tuesday, Wednesday, Thursday, and Friday. Yeah. X2, you're starting on Tuesday, you're working on to Saturday, and so on. So on Monday, you will have the people that are working on Monday, you will have the people that started working on Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. Okay. And then we have more, so this is the questions that I assigned you for the last assignment, assignment 3. That is due on Monday. So the idea is for you to, by looking at the model state. So first of all, you will have to change this into standard form. You add the slack variables and the excess variables. I don't think we have excess variables in this one. But after that, you need to tell me how many basic variables you're gonna have, how many non-basic variables, and then that's going to be based on the number of constraints and the number of decision variables that you have. So we have 3 constraints, and with the slacks, we having 5 decision variables. So 5 minus 2 is 5 minus 3. 5 minus 3 is the number of constraints, 5 decision variables. We had 2 non-basic variables, so that's why we can assign 0 to 2 of them and then solve for the rest. So if I assign S1 and S2 equal to 0, these are my non-basic, I can solve for the rest of them. And then I have values for X1 and X2, and by looking at the plot, I can identify which points associated with 20 and 60. So 20 and 60, that will be point G. And that's what we have here. So we can repeat that process and we will find all the points in this graph. Same thing with this one. So instead of having, now we have excess variables, we go through the same process. It are 4 decision variables, 2 constraints, 4 minus 2 is 2. So we have 2 basic, non-basic variables that we can assign equal to 0. We look at all the possible combinations and we solve it and we find the corresponding point in the graph. Look at this. Let me know if you have questions via email, and we will, I will answer those. Yes. This one?
No, the previous. So this one consists of all the health model over there.
Yes, you don't have to solve this. Yeah, this is a solution, but you don't have to solve it. It's just formulation.
And that is a valid.
Yes, this will be the optimal if it is listed here. Yes, this will be the optimal solution.
But on the part of the
If you fit this into the constraints, the first constraint will be X1 plus X4 plus X5 plus X6 plus X7 greater or equal to 20. You substitute this into those decision variables, the solution should be valid. They will be greater than 20 for that first constraint. Yeah, but in the exam, if I, again, formulate, you don't have to solve. If I ask you to solve, you will be solving using the graphical method. It's going to be very clear. You have to formulate and solve. Okay. Any other questions? Nope, good. So I'll see you on Monday. Have a good weekend.
Thank you.
Okay.